Dr. Saurav Chakrabarty, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So, in the last lecture we are looking at finding the shortest path in a graph. We will be continuing to look at that problem. We will be revisiting our algorithm that we had done, namely the Dijkstra's algorithm, and then we will see how can we improve it with another better algorithm. So, to start with, we work with a graph where we have been given n vertices v1 to vn, and we have been given edges which are pairs of vertices e1 to em. Now, here is an example. We have these vertices drawn in the plane. Each vertex is represented by a node or a circular object with a label on it, and the edges are basically pairs of vertices. So, we represent it by drawing a line between two nodes. So, like a line between A and B represents the edge A B in this graph. So, this kind of drawing is called the undirected graph. So, important thing to note here is that this is an undirected graph. That means, if BC is in this graph, then edge in this graph, then CB is also an edge in this graph. So, there can be other kind of graphs. In particular, we can have these edges with some numbers assigned to it. We call them as weighted graphs. So, these numbers can mean various things depending on how the graphs represent. Also, these graphs can also be directed, meaning we can have some direction on the edges. So, for example, here edge from D to B, which implies that the edge DB in this is in this graph, but since the arrow does not go from B to D, it means that BD is not in this graph. So, this is called a directed graph, and there are weights on these edges. So, it is a weighted directed graph. So, now graphs, as we have seen in the last many lectures, are very useful things and helps us to represent many objects. Many kind of problems can be represented using graphs and all, and there are various properties of graphs that one might want to test or check. One important concept of graph is the distance in graph. So, path is a string of edges that goes from a particular vertex to a particular vertex. The length of this path is usually denoted as the number of edges in that path, and the distance from a vertex u to a vertex b is the length of the shortest path from the vertex u to vertex v. So, this is what we are talking about in the case of undirected graph, graph in which there is no weights on the edges. So, we have each edge and the edges can be directed or undirected, that is fine, but it is unweighted. So, how do we solve this question, or rather what kind of questions can be asked? One of the typical questions that can be asked is that given this graph, what is the shortest distance between a vertex u from a vertex v? Also, one can ask some more difficult questions like what is the shortest distance of any vertex from vertex v? It is like after how many jumps or how many edges can you reach any vertex if you start from vertex v, and these questions can be answered, as we have seen, using the BFS algorithm, the breadth first search algorithm that we had done a few lectures ago. Now, this is the most basic form of graphs, and sometimes one can ask more complicated graphs, in particular when we have weighted graphs. So, in a weighted graph, what is the shortest distance? So, each edge has a real number assigned. That real number can be negative or positive. and the length of a path from a vertex u to vertex v is the sum of the weights on each of the edges in the path. And of course, we can say that the shortest distance from u to v is the length of the shortest distance. So, it is exactly like you are considering a map of a city, and your house is somewhere and your friend's house is somewhere else, and you know that if you go from this place to the next corner of the street, it is some say 500 meters, from that place to some other building it is some 200 meters and so on. And now you want to check what is the shortest distance from your place to your friend's place. So, this 200 meters, in this case the graphs can be the edge weights of the graph can represent the distances in the map. So, this is a question that we asked in the last lecture also, and we have seen some algorithms for it. So, but before that, let us just quickly go over some examples of these paths. So, say if you have this graph G, a directed weighted graph, and consider the path from G to A. Now, here is the path from G to A. It is a directed path. So, a directed path meaning you have to go only along the direction of the edges, and if you note that this path has weight 29. Now, we can also have this path G E B A, which is edge is 23, and we can have this path G F D A, whose weight is 22, and so on. So, it asking the questions what is the shortest path is always a interesting question. Now, the weights can also be negative. You might ask why will the weights be negative, because distance cannot be negative, but as I told you that weights can represent not only distance, but some lots of other things. While modeling various problems in terms of graphs, we might encounter weights of negative value also. So, in this case, say for example, here we can have this path again of age 29, we can also have this path of age 23, we can have this GFDA path of path 22, but we can also have this path which is using this negative edge weight in the middle -5, and then the path's length becomes just 9. So, this kind of situations can happen. We can also have some more weird object, like a cycle can have negative weights. What does it mean? That you have a cycle, means a path that starts from a vertex and comes back to itself, and the total sum of edge weights there adds up to a negative quantity. For example, here again you go from G to A. So, here is a cycle. So, here is -9, 5 and 2, and so the length of the cycle is -2. So, now if I want to go from G to A, what I can do is that I can keep on going on this cycle for infinite amount of time, and then at some point of time I decide to go to A, and which means that I can really get this distance from G to A down to -infinity. Note that our goal is to find the shortest path. So, here in this kind of situation, finding the shortest path always does not make much sense, because I mean you can go there and just keep on repeating this cycle, and the edge weights will go down and down and down. Every time you make a cycle, your edge weight will be -2 plus -2. So, that means if you make this cycle, use this cycle k times, length of the path will be -2k, and then you take the shortest path from G to A. So, this can also happen. So, usually the problems that are given is, say we have been given a graph, say at this point let us assume that the edge weights are positive, and the weights are given as W, V I, V j, and we want to find the shortest path from U to V. There are various assumptions one would like to make. One of them that can be made is that all the edge weights are positive, although there is no need to or no reason to assume that. So, we might want to assume it to make our life simpler, but in general the edge weights might be negative. Also, one can also ask that just to make the definition clearer or more consistent, we should have to ensure that there is no negative weight cycles. So, in the last lecture we saw that there are some kind of This is the algorithm called the Dijkstra's algorithm. So, what is the Dijkstra's algorithm? So, usually what we do is that we write down a table A, B, C, D, E, F, G, H, and basically we start from a particular vertex G, and when you write this particular vertex G, we just write there when you add it. So, we start with G has weight 0. Now, in the next step, this edge E would be updated, all these edges will be updated, and then it turns out that, so G, if G is 0, then what will be the shortest distance to E, shortest distance to G plus the edge length, which is 9. So, I write down here 9 in the case of E. Similarly, for F, I write down 0 plus 1 11. When I leave things empty, it means there is no path from G to this set of elements, this set of vertices, and hence they are infinite. The distance from G to say G A right now is infinite. Now, we find the smallest amount of all of them. In this case, E is the smallest, and in that case we choose E. Now, that means E, this is the shortest distance from E to G, or rather from G to E. Now, if that gets fixed, now we can update the shortest distance from other vertex. For example, D gets shortest vertex distance is, we can go to E and then go to D. So, 9 plus 5 is 14. Similarly, for B, I can go from E and then to say B 7. So, 9 plus 7 is 16, and then from again for C we get 9 plus 1 is 10. At this point, note that the vertices that have red are basically fixed. So, I can like mark it here, the G has been red and E has been red. So, at this point we have the other set of vertices. So, B, C, D and F, and we find this one with the shortest distance from G. Note that whatever is written here, say for example, in the case of B 16 is written here, it means that right now 16 is the shortest distance, shortest path we know from G to B, because we might know that shortest distance from G to E is 9 and shortest distance of B is say 9 plus 16. So, similarly for C, and then we take the minimum of all of this B, C, D and F, or rather whichever things have not been read, and we find that C is the smallest. So, we will choose C and we fix C, meaning from now on it is the case that the shortest distance from G to C is 10, it cannot improve any further. And again when we update it, we can now update all the other things, like we can go through C to B. In that case, to go from the shortest distance from G to C is 10, from C to B is 8. So, now we can go from G to B using 10 plus 8, which is 18 steps or 18 length path. But since 18 is bigger than 16, we do not update it, we leave it. So, still now this path that we have thought, so G to E to B is the shortest path that we have in mind from the G. Similarly, we keep on going like this till we slowly take all the possible edges. So, here is the pseudocode of this Dijkstra's algorithm, and the idea is very simple. We kind of every time update the shortest distance from G to V and keep on doing it. As we saw last time, the running time of this algorithm is order V square. This is a very nice thing. It can find out the shortest distance from U to V in order V square. Not only that, it can find the shortest distance from U to any other vertex in also this order V square, and this is known as the single source shortest path problem. The running time is of course order V square, which by using some more fancy data structure can be improved slightly. But the problem is that this algorithm cannot handle negative weights. So, let us take a small break now. When we come back, we will look at why this algorithm cannot handle negative weights, and we will see how to fix it. So, welcome back after the break. Before the break, we were looking at the Dijkstra's algorithm, and we are talking about why Dijkstra's algorithm cannot work for negative edge weights. For example, consider this graph. So, I have just added a single negative edge weight which is -8. Note that the way in which Dijkstra's algorithm worked is that first it kind of chose this number g and you put some updated the value of g to 0 and we kind of fixed g, meaning from now on we know that the distance of g to g is 0. Then we updated all the other elements which are neighbors of g. So, we updated the value of distance of E as 9 because it is the edge plus the value of g, and similarly for f we updated it to 11. And then consider the smallest element of this which is E, and that element we just pick that. So, we say E and said, oh, now the distance of g to E is forever fixed at 9, shortest distance is 9. Note that here this algorithm has already made a mistake, because as you can see in this graph one can go from g to f and from f to E, and that would have cost us 11 plus -8 which is 3, whereas we have done 9. So, why is it so? So, what is the place where we have made the mistake? The only mistake is that here there is negative weights. Let us quickly revise our proof of correctness of the Dijkstra's algorithm. In the proof of correctness of Dijkstra's algorithm, we could say that the shortest distance from G to E was 9 and that is it. Why was it? Because let us assume that that was not the case. Say G F E is the shortest distance. Now, if G F is the shortest distance, that means and F is not yet marked red, in that case the distance between G to F must have been lesser than the distance of G to E, and I would have chosen F over E. The reason why the distance from G to F would have been shorter than the distance from G to E is because this distance of F to E had to be positive. So, it is something like your home is there and your neighbor's home is there, you want to go to your school. Now, the shortest distance, say somebody says that the shortest distance from the school to your house is 2 kilometers, and then it turns out that no, there is a shorter distance of the length 1.5 kilometers through your neighbor's house. Now, if there is a shorter distance through your neighbor's house, that means this distance of the school to your neighbor's house must be less than 2 kilometers. So, if the shortest distance from your school to your neighbor's house is more than 2 kilometers, then how can be the path that goes through your neighbor's house be less than 2 kilometers? The only idea here is that the distance from your neighbor's house to your house cannot be negative. That is how the intuition works, and that is perfectly correct intuition if the distances or the edge weights are positive. In this case, the edge weights are not positive, and hence we have a negative in -8 there, and that is why the distance from G to F is 11, which is more than the distance of G to E, but the shortest distance from G to E is 11 via F. So, 11 plus -8 is 3. So, this is the reason why Dijkstra's algorithm will fail miserably when there are negative edges. So, question is that how can we find the shortest distance in graphs when there are negative weights? And for that we have to use a different algorithm. In fact, we have to define kind of algorithm. So, this is a very important stage in this algorithms lecture series, where we are entering at one of the most beautiful concepts called the dynamic programming. It is a type of algorithm that requires lot more deep understanding of how it works, and it looks magical to some respect. So, in the next few lectures we will be looking at dynamic programming only. So, just like we had seen divide and conquer algorithm, that was one technique. Similarly, dynamic algorithm is another technique. So, let us see what is the idea. The idea is almost like divide and conquer. It is like decompose the problem into smaller sub problems. Hopefully, the smaller sub problems are easier to solve. Now, for each of the smaller sub problems, solve it and store it in a table, and then finally use the data in the table to get back your solution. So, this is why what is basically the framework of dynamic programming. We will come back to this framework again and again, but maybe the best way of understanding it is via examples. So, let us start with a problem which uses dynamic programming. So, for example, say here in our problem we have given a graph G, and we have been given edge weights, where the weights are from edges to real numbers. Here I do not care whether it is positive or negative, it can be either, and we have been given a particular state S, and we want to find the shortest path from S to any other vertex in G. So, we define this object DLV. What is this? It is the length of the shortest path from S to V using at most L edges. So, you are allowed to use at most L number of edges, and you want to consider the shortest path from S to V. Now, one might ask, what is usefulness of this thing? Of course, what question are we asking in general? What we are asking is, what is the shortest length from S to any vertex, and the length of the shortest vertex or the number of edges in a shortest vertex, shortest path will always be less than say n minus 1. So, final output that we want is d n minus 1 v for all v. But this is where the beauty of this definition lies. For example, say what is d 1 v, meaning what is the shortest distance from S to V using one edge. Of course, it is easy. If the vertex V is in the neighbor set of S, then you can go from S to that vertex using just one edge, and then the shortest path, which is just one edge, will be the weight of the edge S V, which is denoted as W S V. If the vertex V is not in the edge neighborhood of S, then by making one edge move, you cannot reach V from S. In that case, we say the distance is infinite. And here is the catch. If we want to calculate d L plus 1 V, in the shortest distance from S to V using L plus 1 edges. Now, what can that path be? Consider, think of that. You have the S, you have V, and the shortest path that uses L plus 1, at most L plus 1 edges to go from S to V. It can be of two things. First option is that it is the shortest path from S to V using not L plus 1, but even L steps. So, here we have DLV. DLV is the shortest path from U to V using L steps. The other thing that can be there is that to make L plus 1 step and go from S to V, I can make L steps from S to some other vertex W. I have already used L steps, and now from that W I can go to V using an edge. So, that is why we have this one, the DLU. So, it is like going for U, and from U I can take an edge to UV. So, it is something like this, that you want to find the shortest distance of your home from school. Now, you do not know how to solve it. First of all, you ask all your neighbors to find it. So, you will ask your neighbors that, okay, what is the shortest distance from school to your home using just 4 steps. If that neighbor manages to give you the answer, so you know that going through that neighbor's house will give you one possible way of coming using just 5 steps, because neighbor was giving a length of a path using 4 steps, and you will be using one more step from the neighbor's home to your home, and you minimize over all the possible neighbors and you will get the answer. So, DL plus 1 V will become minimum over all possible vertices U DLV means the shortest path anyway which is using less than L edges, plus either you come to your U and then you take the edge UV. So, once you have this kind of a beautiful recursion kind of stuff, let us see how can we use it, and this is what we do. Say here is the graph on the left hand side and I have made a table on the right hand side. Dynamic algorithm always works with tables. So, what is the table is? So, I will just note down here say 1, 2, 3, 4, 5, 6, 7, or in other words it says that what is the shortest distance from S to A, or in this case a G. So, I will look at it from G to A using just one edge. What is the shortest distance from, so this particular thing will say what is shortest distance from G to C using 3 edges at most. So, let us see. So, I have colored this as G. So, this one is a 0. So, it is like I am not allowed to use any edges, and in that case of course, I cannot go from G to any of them except for G. Now, comes the second step, which is I am allowed to use one step. Now, if I want to allow one step, what do I do? Note that every time I can use the same thing, like what is the shortest distance E from G using just one step? Okay, what is shortest distance of G from itself and plus the edge weights. So, we get this set. So, this will update E to F. Just remember here that right now I have not done. This is the same algorithm where we found that Dijkstra's algorithm fails with negative edge weights. So, now let us look at the second step, which is the 2. So, what is the shortest distance for any vertex from G using 2 steps? Now, for E, consider this one G to E using 2 steps is G to F using 1 step, which is 11, plus F to E using 1 edge, which is -8, or in other words we can update this one as this. Note that we have already updated here the distance of G to E to 3 instead of 9 that we had. So, we can keep on doing this like that, and at the end we will have the shortest distance of all the vertices from G. So, here is the pseudocode of this algorithm. This is known as the Bellman-Ford algorithm, and it is exactly what I just now told. It is like you initialize the initial states and then you solve it out using the recurrences. Now, what is the running time of this algorithm? Initial setting up takes order V steps. There we have to update for each of the V's. So, it is like for all I equals to 1 to n, I have to look at this one V, then here again for V, so n or size of V, and for each of the updates I take a minimize over n different objects, so it will be n. So, basically it is like the table has n square number of entries and each entry takes n steps. So, we get order V cube number of steps. Short, Dijkstra's algorithms works with V square number of steps with positive weights, and Bellman-Ford works with negative weights, but running time V cube. To summarize today's lecture, we saw the shortest path algorithm, we saw Dijkstra's algorithm and saw why Dijkstra's algorithm fails for negative edges, and then we looked at Bellman-Ford algorithm, which also manages to handle negative edge weights. Thank you.